Okay, thank you. Yeah, so I'm Peter Sestoft, and as Christian says, I was one of the people helping start this place 17 years ago. I have a background in computer science and published a bunch of books, and in particular, perhaps relevant here, this Java precisely, which is now in its third edition, which covers a bunch of the stuff I'm going to talk about here. So the idea is to talk about Java functional programming and Java streams for bulk data and high-level parallel programming. So Christian has kindly allocated an hour and 50 minutes, but I think we'll take a break midway when enough people have fallen asleep. Also, I want to know how much of this I need to cover. If everybody knows Java functional programming already, there's no point in going through this. So how many people vote for actually taking this part of the talk? Some, yes, enough people, so let's do it. So we'll talk about functional programming too. Although the topic here was parallel programming, but there's a connection, of course. So basically this, this talk is based on this Friday's lecture in a course I'm giving at the IT University. The course is called Practical Concurrent and Parallel Programming, and is based on, half of it is based on Brian Goetze's book from 10 years ago, and is about threads and so on, but there's also stream programming, how to make benchmarks, scalability, data structures, and then a bunch of more advanced things, log-free data structures, transactional memory, message passing, concurrency. But what I'm talking about today is basically the 16 September lecture from Friday morning here, to some extent. The materials I'm using is from this book, the third edition of Java Precisely. The examples are online if you want to look more closely at them. So, what is the connection between parallel programming and functional programming? It goes back a long time. If you take this book by William Birch from the mid-70s, Recursive Programming Techniques, it's one of the first books on functional programming. It has a short section called Parallel Evaluation that just sort of observes that since we're doing everything functionally without side effects, we can easily parallelize the operations. At the time, this was a rather impractical proposal because hardware wasn't parallel except in supercomputers. So this was just a half-page covering this. But it was followed by John, what I didn't mention here, John Bacchus's FP Turing Award lecture about where he named the so-called von Neumann bottleneck and argued that future high-performance architectures would have to be functional. And a lot of work followed in the 80s where there was a research-driven, language-driven activity towards parallel functional programming. Data flow computing, Simon Peter Jones's parallel computers, Paul Rowe's PhD thesis from Glasgow. But this didn't really catch on. Hardware, standard sequential hardware became fast enough to make this not very interesting. But actually now we are in a different situation. We're a technology-driven push towards parallel functional programming. There's this famous paper from 10 years ago, the free launch is over, by Herb Sauter. So basically says there is now a fundamental turn towards concurrency in software 10 years ago. And also an observation by David Patterson from Berkeley, is the inventor of the idea of a RISC computer, reduced instruction set, says that the chip makers are now designing microprocessors that almost nobody can program because they have so weak memory coherence. So there are lots of cores on the same chip, but they're very cheap very weak cache coherence, and basically need to be at a much higher level to program things well. And this higher level turns out to be Java. We're in a situation now where if we want, we do have multi-core chips. If we want to be fast, we need to be parallel. To be parallel, we need to have something like streams, a high-level concept. And for this parallelization of stream computing to work, we need functional programming. So mysteriously, Java as a prime object-oriented platform has needed to introduce functional programming to obtain streams, to obtain parallelization of streams, to have a fairly easily understandable parallelism. As I showed in this course overview, this is not solution to all problems. There are 13 other lectures here. There's a reason for the 13 other lectures. So streams don't solve all problems, but they solve a lot of problems well. Okay, so let's take a look at the take a short first lecture on functional programming and then on streams. So new in Java 8 from 2 years ago are lambda expressions. Well, this is a lambda expression that says I am a function that takes an argument s of type string, and then I promise to return the length of s. We can also have so that's a complete expression of function type in Java. We can write more or less the same thing like this by saying string colon double colon length. That's a string class's length. Interesting. Length. What is this? Length method. Okay, and then these things have types. So possible types for those two things is function from string to integer. So we can have functions. And then this is used in streams, where we can say that if SS is a stream of strings, then we can map this function that takes a string and returns its length. We can map that over all the elements in the stream of strings. Then we obtain a stream of integers. So that does a lot of work in one go. And we can take a stream like this SS stream of strings and parallelize it and map over the parallelized streams. And then these operations happen in parallel. And here, of course, the functional, so this is functional programming, a higher order function with a function argument. And of course, the absence of side effects starts to be important here when we do things in parallel. The other thing that Java has got, apart from functional programming, streams, parallel streams, is parallel array operations. So something, a very simple thing to initialize an array in parallel, taking an array that to initialize and a function from index to the value at that index. And that initializes the whole thing in parallel. And then there are so-called parallel prefix operations, which are a really clever invention from around 1990. So, so what is functional programming actually compared to other sorts of programming? I think there are three things that characterize the functional programming. We work with immutable data instead of objects that have state. We have recursion instead of loops, and we use higher order functions. A higher order function is a function that either takes a function as argument or returns a function as result. So here's an immutable list of T represented as a list class that has a local nested class of a node, and a node contains an item here of some type and a link to the next node. So that's a list, a singly linked list of U values, and the list class contains a reference to the first node or null if the list is empty. Everything is final here, so this is immutable. All operations on these will have to create new lists instead of mutating existing lists. So just to make it clear how this sort of thing works in that kind of world, here's the same stuff repeated, and a little method here that takes an item and a list and puts the item in front of the list. So here's a list of integers represented by a list object of some sort with a reference to a node, with a reference to a node, with a reference to a node, with a null at the end. So this is how lists were represented in Lisp in 1960. So this is a very old idea. We typically call this the head and the rest the tail of the list, if it's non-empty. So, so how do operations of this sort work? So let's there's a small program with a number of variables, empty and list 1 to 5 of type fun list of integer. So we start by creating a 3-element list where we put 9 in front of the result of putting 13 in front of the result of putting 0 in front of the empty list. Then we have this list in memory. If we now try to put 7 in front of this list, so list 2 is 7 in front of list 1. It will not mutate this one, but simply create a new node 7 that links to the old list 1, and then that's our list. If we want to put 8 in front of the same list up there, we just create a fresh node, points to the same thing there, and refer to that. If we now imagine there's an insert method, insert on list 1, so we take this list here with 3 elements, and we want to insert at position 1, this is 0, 1, 2, we want to insert at position 1 the value 12. Then we'll have to create a new node 12 that points to the tail of that list, and then basically duplicate the node 9 here. And if we now want to take list 2, which is this one here with 4 elements, and remove the third element, so this is 0, 1, 2, 3, so we want to get rid of the 0. Basically we need to duplicate the entire list. It walks down the list 2 thing here, counts 0, 1, 0, 1, 2, 3. That's the one we don't want. So the last one to retain is this one. We can't just change this pointer because, first of all, it's final, so we can't change it, but also it would destroy all the other lists. So we basically have to duplicate the elements here. So, so how on earth is this sort of thing like list 1 insert implemented, the one that inserted 12 here? It looks a bit difficult, but actually with a bit of recursive thinking, which goes back to, for instance, Birch's book from 41 years ago, it's very easy to implement. So here's the workhorse here is this insert on the node class that inserts at index I, inserts item t, provided we want to insert it in this list of nodes x's here. So if I is 0, that means we want to insert it in the front. We simply create a new node with the new item and the old list. If I is not 0, then we create a new node, so basically duplicating the node, where we take the old item from the list, and then we call recursively with insert -1, insert this item at position the I minus 1th position in that list, which is the tail of the given one. So using recursion, it's completely trivial to implement this sort of non-mutating creation of new objects. So this is well known in functional programming. It's a little unusual in object-oriented programming, but very easy to learn, I think. Let's see. So, immutable data, that's what we had here. And so this is supposed to illustrate the use of how to use and compute with immutable data. There's something bad and something good about immutable data. Immutability obviously leads to more allocation, as you can see here. When we want to remove the element number 3 from list 2, we actually have to duplicate a lot of stuff, potentially a really, really large amount of stuff. So sometimes that's bad. But actually today the allocators and garbage collectors are fast. That's not a complete excuse. You may be in a situation where this is completely unacceptable. But whereas 30 years ago garbage collectors were slow, they are really, really, really well engineered today. But the good thing, so that's bad thing about immutable data. Good thing is that they can be safely shared between different methods. Where it's harmless to hand out to another method a reference to list 2 because nobody can destroy my list while I'm using it. So actually it leads to less allocation, as you can see. We actually get less allocation because these seems to be 3 lists here, but they actually share the tail there. So a lot of defensive copying is no longer needed. And absolutely most important thing is that it's automatically thread safe. If nobody can change it, it means that no other thread can change it. So it's absolutely safe for others to access it while I'm using it, and it's absolutely safe for me to access it while I've handed out a link to this data structure to somebody else. there's also a really subtle point about the semantics of the final modifier in Java and the memory visibility effects. So that's, I'm not going much more into that, but it's actually necessary in a multi-threaded context to either have final fields in objects, or to have enough of them volatile, or to take and release locks for visibility between threads. But let's, yeah, this is fortunately designed correctly here. And in the .NET world, it's much less clear what actually works. Okay, let's get a little more into functional programming here. So we already saw something like this here, a function that takes an argument s and returns the result of parsing this. So a function, so the thing in the box is a function. It's an expression, first of all. The value of that expression is a function that takes a string s and passes it as an integer and returns the parsed value. And such a thing can be assigned to a variable FSI1 here of type function from string to integer. And then later on I would like to apply this function. I do that by calling .apply on some string, and it will return 4,711. block, and within that block I can have a return. So I can have a whole method body there, and I can give the type of the string also. So I can also have two argument lambda expressions, so one that takes a string s and an integer I and returns some other string computed from that. So that's similar to the types you would know in Haskell or F#, string times int to int, the function that takes a string and an int and returns an, no, that's a misprint, of course, it should be a string here. Right, too bad. So one can do all sorts of other lambda expressions without arguments and so on, but they have funny names here. That's perhaps the most important thing. That a function from string to string, string to integer, that's clear what that is. It's a function from string to integer. But in Java there are also supplier. A supplier is basically a function from no argument to something. So a plier of strings is a function that takes no argument and returns something. And the consumer is the opposite, one that takes an argument and doesn't return anything. So that's called string to unit in F# and other functional languages. So let's skip this. So lambda expressions is one way to write function valued expressions. Another one is to write to use method reference expressions. We already saw them before, but string :char add is the char add method from the string class. That's an instance method, and therefore this is actually a two-argument function. It takes a string, which is the instance, and the index I, and returns the character at that point. So that you could write it as a lambda as well. And similarly for integer parsing and so on. And you can write some funny things like here's an object, a string object with 16 characters, :char add, that's a single argument function that takes an integer and returns a character. So that's a simple way of converting a number to a hex digit. And so on. And there are funny things also to create. You can refer to constructors and to array constructors, but we won't use that. The interesting thing about Java's design is that lambda expression or method doesn't have a type in itself, so must have a targeted function type. That's because of the whole inheritance system of subtypes. It's impossible, unlike in ML or F# to infer a type for something. So that means that a lambda or method reference expression must appear in one of these four contexts here. Either it must be the right-hand side over here of an assignment, and then the targeted function type is the type of the assigned to variable. So this thing in itself doesn't have a type, But once I assign it to a variable that has a type, then it has a type. So that's why we need we need a targeted function type. Otherwise, I could use it as an argument to a call, and then the map method has an argument type, and that's the targeted function type. Or I could use it in a cast, and then the cast type, of course, is the targeted function type. Or I can use it in a return statement, and then the targeted function type is the enclosing class's return type. So these are the only 4 places one can use a function type. Let's take a look at a higher order function here. For instance, our list class might have a map function. A map function is a higher order function that takes a function as an argument. So we are inside the fun list T class here, and the map function takes as argument a function that maps T's to U's. And then map will return a fun list of U's. So basically take the given list of T's, transform every one of them into a U, and return that list. And again, it's fairly trivial to program it. The machinery is inside the node class here, that if the list is empty, then the result is empty. Otherwise, we apply the given function to the first item in the list and map F over the rest of the list. So that's a general behavior, very similar to exactly what you obtain with the template method pattern. And we can use a map like this. For instance, if we have some list 5 that has element 7, 9, and 13 from the previous slide, we can map on that the function that multiplies by 2.5. This is a list of integers, and this is a function from int to double, so we get a list of double. Which contains these 3 elements multiplied by 2.5. And we can apply all sorts of other things, like a predicate that takes an integer and returns a boolean, whether this thing is less than 10 or not. And it will return true, true, false. And that will be a list of booleans. Okay. Another well-known thing is reduce. Here I've given only the code from the node class. Reduce starts with some neutral value x0, and then there's a function that takes 2 arguments, a u and a t, and returns a u, an operation here, and a list of t's. And if the list is empty, it returns this one, x0. Otherwise, it calls reduce on the result of applying the operation to the x0 and the first item, and the operation again, and the rest of the list. And that's a simple way of computing summations. For instance, if we have a list and call it on reduce, so x0 is 0, and the function is add, so it takes an integer and an integer, and it returns an integer, then reduce computes the sum. And there are all sorts of interesting things that can be computed this way. So this, of course, map and reduce are well known from the map-reduce framework, and map-reduce framework from Google is just functional programming at a very, very large scale. Let's skip this. Also this. So how is this fit onto Java, which is not a functional language? It's born as an object-oriented language with interfaces, classes, inheritance, methods, and all sorts of things. And the way they've done that is relatively clever. It's not as beautiful as in Scala, which has a very, very nice integration, but that's also a rather complicated language. So they define that a functional interface is an interface, no, completely ordinary Java interface that has a single abstract method. And then, of course, it may have default and static methods in Java 8 also. So the type of functions from T to R is basically this thing that has an apply method and an abstract apply method. The abstract method takes a T and returns an R. So that's a function from T to R. And this is, in C# it's called func_tr, and F# it's T to R, and almost all functional languages use this notation, which is the mathematical one. And then there's the consumer interface. Consumer of T has a single abstract method, accept, that takes a T and returns nothing. It's called an action in C#, and it's called T to unit in F#. The ugly thing about Java is that it has a huge number of functional interfaces. So the ones you really care about is function and consumer and supplier and this sort of thing. And so basically, and then functions with 2 arguments and so on here. So these are single argument, single result things, or 0 argument, 0 result, 2 arguments, and so on. And then there's all this crap, and the crap has to do with these are so-called primitive type specialized interfaces. And so this causes a lot of confusion, but it's there for performance. We have both a function from T to R, this interface here, and another interface called int function R. It's hidden somewhere in this list here. An int function R takes an int and returns an R. So we could both. So this function on the right-hand side that takes an I here and returns # plus I, which obviously takes a string, converts I to the string, and concatenates the result. That's a function seemingly from integer to string. But it actually has 2 different targeted types, and that's why we need the targeted type, targeted function type. It can either be a function from integer to string or an int function that gives a string. That both work fine. So what's the difference? The difference is that if we call f1, this up here, the function integer string, call that on an integer like 42, this integer will be boxed because the argument type here in function integer string is this capital integer, the object integer. And boxing the integer will take 40 nanoseconds or something like that, which is quite a long time. So it will need to allocate an object in a heap, and that takes both time and memory. But time is the worst in this case. Whereas calling f2 apply will avoid the boxing because the argument type is int. So you can't see it in the syntax. If you can certainly write this f1.apply 42, and the compiler will not complain. Only at every invocation at runtime you will have this cost of allocating an object. So the whole thing is there purely for performance. It's to avoid the penalty of allocating this capital integer object in the heap. So all this stuff here was there to obtain good performance, and that's quite annoying. This is avoided automatically in the .NET platform because it has a much more sophisticated runtime where interfaces and types can be specialized to primitive types, not only reference types. So the root of the problem is that in Java is that a generic type like this function tr, whatever you replace, whatever you insert for t and r must be reference types. Can't have lowercase int here. The runtime system is too simple-minded. But in 2022 or something like that, it may be a different story. Okay. Nevertheless, if you can sort of abstract from this horrible problem, then it's a very nice piece of engineering, as I'll show. So let's see. Here's a complicated example of using higher order functions. I think we'll skip it in the interest of getting to streams. But what's actually quite beautiful is that in a very, very few lines of code, you can write sort of a converter from very large numbers to the corresponding English or French or German text by using a bunch of higher order functions and very simple stuff like this, basically like this over there. But I'll skip that. So basically, we are here to talk about streams. Okay, so now I hope you get an impression of what that functions can be. You can have expressions that are function valued and pass functions to other functions and to methods, and that you can program with immutable data. So streams. A stream of t is a finite or infinite sequence of t values, possibly lazily generated and possibly parallel. So you can have stream of string, for instance. There are some predefined stream methods like map that takes a stream and transforms all elements on the map of the stream into a new stream. Flat map, reduce, filter, and so on. Things that are known for functional programming. These all take functions as arguments, so they're higher order functions, so very generic things that are parameterized with other functions. These can be combined into pipelines, so you can transform a string in several steps, as we'll show. And it turns out that the Java implementation optimizes and parallelizes these pipelines really, really well. It's extremely well implemented. It's implemented as a library, but it's based on knowledge about what the JVM actually does, the JIT compiler does. It's quite similar to iterators in Java or enumerables from C#, but the implementation is very different. It looks very similar to the extension methods that you find underlying .NET's link language integrated query. So let's look more closely at some stream operations here. So to create a stream of integers, you could simply say stream of, and then enumerate a bunch of integers. So this is one of these variable arity or methods that gives you a 3-element stream of the, so a finite stream of the 3 integers 2, 3, and 5. And then you can apply a filter to a stream. So S filter P will return a stream of the x's where p.test x holds. So P must be of a type predicate of integer. So for instance, you can compute the S filter where P is this function that takes an x, computes the modulo 2 remainder, and if that's 0, then it's true, of course, otherwise false. So this is basically the predicate is a number even. So this gives a stream containing only 2 because 3 and 5 are not even. You can map a function over a stream, and that is the stream of results of calling f.apply x for all x's in the stream. So here, if we take the function f that takes an x and returns 3 times x, we get the stream of 6, 9, and 15. So 3 times 2, 3 times 3, and 3 times 5. Then there's flat map. That's a flattening of the streams created by calling f.apply x for all the x's. So basically, now f is a function that takes something from the stream, an integer, for instance, and produces a new stream instead of a new integer. So let's take the function that takes an x, an integer, and returns a 2-element stream containing x and x plus 1. So each call to this function will produce a 2-element stream. And that gives us the concatenation of these. The first call gives 2, 3, and the second call gives 3, 4, and the third call gives 5, 6. So that's flat map. And then there's find any, applied to a stream, returns some element of S if there is any, or else the absent option value. So S find any might give any one of these 3. For a parallel stream, it's not obviously a good idea to return the first one. It might be that element number 23 is computed first, and therefore better to return that. And then there's the reduce, similar to the one I showed you an implementation of for integer lists. Reduce takes a neutral element here, an operation, and basically computes, if we write this up here, if we write this disgusting up.apply xy, if we write that in a nice manner as x diamond y instead, then what reduce computes is x0 diamond s0 diamond s1 and so on for the whole thing. And if that operation is associative, then this can be computed very fast. So s.reduce applied to 1, and the product function gives a multiplication function gives the product of the elements. Applying it to 0 and plus will give the sum instead. Applying it to minus infinity and the max function will give the maximum of the element and so on. So lots of things can be computed by reduction. similar functions are everywhere. So what JavaStream calls map is called map in Haskell, Scala, F#, and Clojure, and select in C#, because their thinking was associated with the SQL database language at the time. So that's sort of the outlier here. Flat map is called flat map in Haskell and Scala. It's called collect in F#. It's called selects many in C# and mapcat in Clojure. Reduce is a special case of a fold left in Haskell, fold left in Scala, fold in F#, aggregate in C#, and reduce in Clojure. And basically many of these functions go back with strange names back to the 70s when people started thinking about this. So let's see what we can do with streams. So now we have a repertoire of functions there. And let's see, just to convince you that they are quite cleverly implemented and can be used for more than you would imagine. So here's let's assume our problem for today is to count the number of prime numbers between 0 and 10 million or something. So from 0 up to 10 million. And so a classical C programmer would write this code here. We have a for loop that goes from 0 to 10 million, and we call it isPrime function. And if that returns true, we increment count. So that seems obviously the most efficient thing you can do. You could also use Java 8 streams. If you are sort of a array-bit functional programmer, you would say int stream.range, 0 to range, that creates an int stream of 10 million elements, and then you simply apply the filter function to that and say, I don't only want those numbers that are primes. And then you get a stream of integers out here, and then you count how many elements there are in that. That's obviously correct. We take all the numbers, we take those that are only primes, and we count them. Okay, but obviously must be inefficient, such a stupid way of doing it. But we could also say, maybe there's hope. We could insert parallel here. So we take 10 million elements, we parallelize that stream, and in parallel then we execute the filter and count operations here. And this provided, of course, that isPrime is thread safe and not... and the simplest way of making that thread safe is to make it stateless. So the performance results are somewhat wonderful. Here's 2 columns. One is for this machine, the Mac with 4 cores, and here's for an AMD Opteron with 32 cores, a very big server. The sequential for loop takes 9.9 milliseconds now. That's only for 100,000 elements. The sequential stream takes exactly as much time. So this funny way of writing it is completely the same as that in terms of performance. And the great thing, of course, is that you get parallelization for free here. The parallel stream thing takes 2.8 milliseconds on that machine. That's a speed up of 3.6, factor of 3.6 on a 4-core machine, which is not bad. So by programming functionally and sort of naively, declaratively, we actually obtain parallelization very, very cheaply. Results are even better. Okay, I should maybe say that, of course, you could take this loop here, take this thing, and parallelize that explicitly by creating threads or creating tasks, futures to execute on the Java thread pool. You could do that manually. It's vastly more complicated than inserting these 11 characters, but you could try and do it. And actually, I was able to get a computation was slightly faster than the parallel stream, but only slightly. So the implementation of this is extremely good. Obviously, it doesn't create 10 million elements up front. It creates them a block at a time on a task, and so on. The performance on the AMD server is even better. So first of all, it's wonderful that this very expensive server is 4 times slower than the laptop for the sequential code. But you see there's, again, not much difference between the for loop and the functional code. The parallel functional code is 24 times faster for free, almost. And the best hand parallelized code I could write was not as good as the parallelized loop. So the people who implemented this stuff have really, in Java, the Java libraries and the Java virtual machine really know what they're doing. Here's another example we'll take before the break, and then take a short break, and then look at some more horrible things. So obviously, maybe I'm cheating here, that the cost of this is prime thing is so high that whatever cost there is of creating elements and so on is trivial compared to the cost of is prime. So let's do something else where the cost of the loop operation is more obvious. So let's assume we want to compute the sum of this series, 1 plus a half and a third and a quarter and so on, up to almost 100 billion here. So obviously you could write a for loop here, goes from 1 to a billion, and compute floating point 1.0 divided by I and add that to a sum. Or you could do it backwards. And already here you should hopefully think that things having to do with floating point are ugly and likely to lead to surprises and complications. So, will these produce the same result, first of all? No, unlikely, because if you add the large numbers first, like this one does, by starting with small divisors, then you will have less room for the less significant bits of the ladder numbers. This might be better. At least some numeric textbooks will tell you that this is better. But there's another way of doing it using pipelines streams. You can create an integer stream of the 1 billion elements and then apply this map to double function that takes an integer and returns 1.0 divided by I, and then you get a stream of doubles, actually a double stream. And then you could compute the sum of that with a built-in function for that purpose. Or you could even do it in parallel. And again, you might wonder, would these produce the same result? Because here we are doing it in that order, and here we are doing it in any sort of random, strange order, depending on the scheduler. It turns out that the for loop, the forward for loop is the fastest, 5.4 seconds. The backwards for loop is surprisingly much slower, and considering that the only thing it does different is to subtract an integer here, and you would think that the floating point division was actually the cause of most of the work. So, and the stream is slower. So here the stream is clearly slower, 8.5 seconds instead of 5.4. The parallel stream is faster than all the others, actually by a factor of more than 4. The machine has 4 cores and hyper-threading, so that may be the reason. But what's really interesting here is the results. You see that the result of the forwards for loop and the backwards for loop are really different. They are equal until that point, but then the last 4 digits differ. What's mysterious is that the stream and the parallel stream produce exactly the same result. And what is the real result? It's this. And you find that the stream-based result is much, much closer to the real value than the for loop. So what is that kind of magic? It's presumably because what we did here was to use the built-in function .sum on the double stream class. They probably implemented that using something that's called Kahan sum, where instead of a single addition, you use 3 subtractions. This is very mysterious, but there's an enormously clever way of computing sums in IEEE floating point numbers that doesn't lose any precision except 2 units in the last place. And that's what we have here. So it means that not only is it much easier to write this code and parallelize it than to write this or that. It's not too difficult, but the results are actually better. Now, anybody could actually implement Kahan sum, but you don't want, when your task is to, let's say, compute the net present value of a cash flow, then you are focused on discounting and all sorts of things, and you don't think that addition is a problem, and you don't want to muddy your code with addition, very complicated looking code that actually just achieves addition. But when the whole work is hidden inside this method with implementation is probably 8 lines or something like that, it's not so bad. Then you actually can get both reasonable speed. It is slower because it does more work, but vastly better results in one go. So streams are surprisingly, I didn't know this. I made this example for teaching, and it turned out, of course, well, I was interested in results here. This parallelization happens in a random way from different runs, give different results you would expect, but due to this Kahan thing, it doesn't give the same result every time. So let's take a break here and then get back to a few more bizarre things with streams. I said this precise sum is used, compute used Kahan sum, and it's not really very mysterious. It looks like this if you want to implement it yourself. So instead of one addition per element, you perform one subtraction, one addition, one subtraction, and one subtraction. And mathematically, these things cancel out. But in computer numbers, in floating point numbers, they don't. So this way of summing things is more precise than just using plus operations. The thing is invented by William Kahan, who's the designer of the IEEE floating point standard. So he knows what he's doing. Okay, so it turns out that we can get wonderful speed-ups and so on using streams, but we can do it only if we have no side effects. So you can look at the Java documentation. It says side effects here. Side effects in behavioral parameters, that is, the function arguments are in general discouraged, but I think a more precise term would be catastrophic, because almost all, even innocent-looking uses of side effects in this function argument will produce very mysterious results if you try to parallelize the operations. The Java compiler cannot enforce purity or the absence of side effects, and the Java runtime cannot detect them because of the language design. So everything, sanity relies on the developer's discipline here. Okay, let's take a look at some stream operations. There are many ways of creating streams. We already saw this stream of and then a list of arguments. This creates an int stream. But what this also reveals is that in addition to stream of T, the generic stream of object references, there are primitive type specialized versions of the stream class called int stream and double stream and long stream. There are only those 3, for the exact same reason that there are primitive type specialized versions of the function interfaces, namely that the representation of an int stream avoids boxing of the integers. So we can create a stream from an enumeration here of the elements. We can take an array and turn it into a stream. We can take a collection and turn it into a stream. And we can take a, for instance, and turn it into a stream of map interest, the key and the value. And using these things, one can do a lot of stream-based stuff on the standard lists, standard classes, arrays, collections, maps, and so on in Java. As we talked about in the break, this is sort of quite irritating because these things are mutable. And then you have to take them over into the immutable stream world compute and perhaps create a new collection or a new map afterwards. So it would, some of these things would be much more beautiful if Java had immutable collections, which it doesn't yet. But apparently people are working on that. So these create finite streams, all of these operations that are ordered, sequential, and lazily generated. So if we have an array here of 1 million elements, we don't materialize a stream of 1 million elements. Stream elements are generated from the array as they are needed. And then there are a bunch of special case streams. You already saw this int stream range from something to something, which creates a stream of 10,000 integers starting with 0. The random a random object has an int method that creates an element, a stream of 10,000 random elements here. From a buffered reader, you can create a stream of strings. It's lines, but that's, I think, the only one that's attached to the I/O system. And from a bit set, you can get a stream of the integers represented by this set. And then there are functional iterators to generate infinite streams, imperative generators for infinite streams, and stream builders. So let's take a look at generators of the various sorts. So there's the functional way of creating a infinite stream of integers is int stream iterate that starts with a 0, and the next element is always obtained by applying this function. So this will that adds 1. So this will be the stream 0, 1, 2, 3, 4, and so on up till the maximal integer, and then it will be a most negative integer, and so on. So it will actually be infinite. It'll just cycle around, wrap around, because it's 32-bit. But you can do the same thing imperatively by the generate method. The generate method takes as argument an int supplier, so that's a function from no argument to an integer. It's called get as int, and it can have local state like this. So there's a next field inside this anonymous inner class that's created here, and that will actually create the same stream as this one. And a third way of doing the same using a hack. If I want to, instead of using an anonymous inner class created from the interface here, I can use a lambda expression. That is a function that takes no argument and returns an integer. Everything that's captured in a lambda must be final. So I cannot have a next variable here that is that gets mutated in there, but I can have a final array reference of a singleton array. That is the thing I mutate. So this is a hack to write this in a different style. The most efficient of these three is the functional one. So there's no need to do this complicated stuff if you can avoid it. And also it's the only one that's parallelizable. If you try to take this nats2 stream here and put nats2.parallel and then map or something, then multiple threads will update this field at the same time, and you lose updates. So, so these are not thread safe. You could make it thread safe, but it will not be more efficient. So use the functional one when possible. The stream builder is a way of creating finite streams up front. So we might have a class int list or our list from before, list of t, and I want to turn that into an int stream. And we can do that by giving it a stream method that, or static method here that takes an int list and returns an int stream using a stream builder. It's very similar in the way you use it to a string builder in Java. You create a builder object, and then there's a simple loop that goes through the list and puts the elements of the list into the builder and return sp.build. This is, has some drawbacks. It's eager. No stream element is output until the whole thing has been built. So if you have a very, very long int list and you apply .stream to it and you only want the first 3 elements of the stream, then you will actually create the whole stream first and then take 3 elements and ignore the rest. And it also only, for this reason, of course, works only on finite finite sequences. On a cyclic list, it would simply go on forever. But nevertheless, this is a useful way of doing things. Okay, let's try to use streams for something pretty somewhat more mind-boggling than adding numbers. So let's assume we have this simple programming exercise of computing all n permutations. So for n equals 3, we have the 6 permutations. Numbers are 0, 1, and 2. So there's 2, 1, 0, and 1, 2, 0, and 2, 0, 1, and 0, 2, 1, and 0, 1, 2, and 1, 2, 0, 1, 0, 2. These are the 6 permutations of 3. And we can do that with streams where we basically exploit all sorts of wonderful things like laziness and recursion. So we write a function, perms here, that takes 2 arguments, a bit set of the numbers not yet used in the permutation, and then an int list, which is an immutable incomplete permutation. So the incomplete permutation may be, for instance, 0, 1, the list 0, 1, and then the bit set will contain 2, which is not yet used. If the to-do set is empty, okay, and the result of the entire thing is a stream of int lists, a stream of permutations. Each of these is an int list, and this is a stream of int lists. Okay, so it's relatively simple but slightly mind-boggling. If the to-do set is empty, then actually all the elements that must be in this one are there. So it's not an incomplete permutation, it's a complete permutation. So we create a singleton stream containing this permutation and output that. Otherwise, there's some element in the set here, and then we can create a stream. So that's a bit set. We can create a stream of all the elements from this one and box that, so we get from an int stream to a stream of integer. And then we can apply flat map to that. It means that for every element in this set of remaining work, we call the permutations function recursively now on a set where we have removed the element r and only that, and then on a new partial permutation where we have added the element r to the partial permutation. Each of these calls will produce a new stream of int list, and the flat map will create a stream of streams of int list and then flatten that to a stream of int list. So this generates basically all these permutations. If you call it like this, you create an empty bit set here, and then flip all the bits in it, so it becomes a set of the elements from 0 to n minus 1, and then you call this thing on the set of 0 to 2, for instance, and the empty permutation. That creates all permutations so in this sort of standard functional style in a sense, but it's fairly elegant also in Java to do it in this functional style. Okay. So how does it work more graphically? We start out with a set containing all the elements here and an empty permutation. Here, like the 3 elements and the empty permutation, and then there are 3 recursive calls corresponding to 0, 1, and 2. So the first one is called with R0, and then the bit set where this has been removed, and now the R has been moved to this one. And there's another recursive call at the top level where R is 1. And here's the set with R with 1 missing, and the 1 has been moved there, and similarly the third one here. And then there's this tree of recursive calls, and when you get down to an empty to-do set, then you output to the stream these things. And that actually happens lazily. So even if n is 10, then the result here has 3.6 million elements. And you don't want perhaps to generate all of them up front before you look at the first one, but it's generated lazily because this thing generates lazy streams, generates a lazy stream, and flat map lazily maps this thing over something that generates lazy streams. So it's actually a very, very efficient and memory efficient way of doing this. But there's more fun to say about that, because what is a permutation? You can look at it as the solution to the problem of putting 3 rooks, torn, on a chessboard so that they can't attack each other. So here are the 6 permutations. Here's the first permutation with a rook in row 2, rook in row 1, and a rook in row 0, and another one with rook in row 1, rook in row 2 and rook in row 0. So these rooks or pawn kind of attack each other. And so everybody who's something in computing has solved the n-queens problem at some point. How to place n-queens on a chessboard so they can't attack each other, which is vastly more complicated than placing rooks. But it turns out to be almost the same, actually. So if you want to solve this problem for queens, which can attack on the diagonal in addition to the rows and columns, we simply need to take our program here and insert a filter operation here that throws away all those R's where all those candidates here where it would be unsafe to put a queen in front of the partial solution. So here's the whole change that's needed to turn this permutation program into a queens solver instead. We simply take all the missing numbers here, those that are not yet part of the solution of the queens puzzle, and filter that away, take out only those R's where it's safe to put the queen in this row in front of the partial solution. And the safe predicate can be written like this with some recursion down here. So that's the extra code here. So that's a very simple way of solving the n-queens problem. Doing this with imperative backtracking and an array is somewhat more mind-boggling to get right. And it's a absolutely wonderful thing about this is that you can put in .parallel there, and then you have a parallel queen solver. And such a thing I've never seen written imperatively. Of course, nobody needs to solve this n-queens problem, but a Sudoku solver, any other sort of combinatorial optimization thing that tries to solve combinatorial puzzles can be written in the same style. So it's a very powerful paradigm. Basically, what you get here is backtracking in a somewhat mysterious version, perhaps, but you get backtracking for free. So, and now the great thing about this is that the function here returns a stream of solutions. Now we can use that in many different ways. So if we just want to know how many solutions there are to the 8 queens problem, we call queens 8, we get a stream of int lists, and we count the number of int lists and get 92. If you want to print all the solutions, we say queens 8 dot for each and print, provided there's a reasonable toString method on the on int list. This gives the desirable result. We can print an arbitrary solution if there's one. So queens 8, find any. If you try to solve the 17 queen problem or something, it takes a while to generate all the solutions. If you just want any of them, it will find the first one that print the first one it found. And you can print the first 20 by say queens 8 limit 20 and then print, for instance. All of this, of course, is much harder in an imperative version. Basically, if you take John Hughes' Why Functional Programming Matters paper from 1989, then you will find this sort of arguments there, that both backtracking and all this about using the stream of results in some way. He works in a lazy functional language, and that's basically similar to a lazy stream here. So that's a cheap way of having this separation of concerns that Dijkstra wrote about in the 70s. The production of solutions is here completely decoupled from the consumption of solutions. Right. Okay, maybe 8 queens problems, 8 queen solutions are not really what you need to do in your job. But in finance, there's something called van der Korput numbers, which are used for simulation. And for instance, Black-Scholes options evaluation, usually we can use it, either use pseudo-random numbers or use the van der Korput sequences. So the van der Korput sequence is this one: a half and a quarter and 3/4 and 1/8 and 5/8 and 3/8 and 7/8. So if I try to write on this one. So you have the number line between 0 and 1, and you start with this one, and then that one, and that one, that one, that one, that one, and that one. So, and so on. The next one is this, and then somewhere here, and so on. So that's a not a random sequence, but it's a sequence that's where any prefix is dense and uniform in the interval from 0 to 1. So how can we generate these things? We want to generate them basically and run and consume them, generate them lazily. So there's a nice trick. If you look at these numbers and write them in binary, as binary fractions, you see half is this, 0.1, a quarter is 0.01, 3/4 is 0.11, so a half and a quarter, 1/8 is 0.001, and so on. If you now look at these, read these numbers from right to left instead, you see here 1, 2, 3, 4, 5, 6, 7. So basically, these are just which means that the van der Corput sequence can be almost infinite van der Corput sequence can be generated in this way, that we consider all possible divisors from 2 to the 31, or 2 to the minus 31 actually, and turn that into a double stream, flat map this thing down here onto it and concatenate the result. And then you get 2 billion of these things, potentially, so because it's generated lazily. And the only thing is that it uses this function to reverse bits in an integer, which is standard. Then, so we have now looked at a bunch of sort of pipelines here. So in-stream rain generates something, then we consider it as something else, and then we flat map on it, or we map on something. So on, we transform strings, but they also need to end up to being something, and you can use reduce for this to get from a stream to a number or sum or this sort of thing. But sometimes it's inefficient to use functional reducers, and there, for this reason, Java has so-called collectors. I see there's a whole talk about collectors tomorrow, so I won't say too much here, but a completely wonderful collector that's built in is the joining collector on stream of string. So a standard problem is to convert some object into a string representation. In particular, turning one of our int lists into something like the string left bracket 2 comma space 3 comma blah blah, and not having a comma there and so on. So I've written this sort of code 1,000 times, I think, over the last 35 years, where you try to convert something into a string. This is now no longer necessary, because if you have a way of turning this int list into a stream of something, then you can, so this is a stream of integers, I think, and then let's map that to a stream of the strings representing those integers, and then use the collector that puts a left bracket before the result, a right bracket after, and comma between. Then you no longer ever need to write this sort of complicated logic that handles the first or the last element especially. We just need to write the stream builder here, which is completely trivial because it loops over all the elements. And if you want to build a string, you can't build a string partially in Java. You can't build a string lazily in Java, so you need to create the entire stream up front anyway. So nothing is lost here. Okay. So there are many sort of different dimensions to streams. A stream may be finite or it may be infinite. It may be lazily generated by iterate or generate, or eagerly generated. Of course, all infinite streams must be somehow lazily generated. They can't be eagerly generated. A stream may be ordered, meaning that map, filter, and limit preserve element order in the result, or unordered, which accepts that the output of map may be not in order, which I think is probably not something you want very often. A stream may be sequential. All elements are processed on a single thread versus parallel, which means that elements are processed chunk-wise on multiple threads on a thread pool. So how are they compared to Haskell? Haskell lists, the paper by John Hughes, Why Functional Programming Matters, I mentioned before, used lazy lists, primarily lazy trees. There's a big difference, which is that Java streams are used once, so you can't consume the same stream twice, whereas a Haskell list can be consumed multiple times. So there's some really beautiful algorithms in Haskell that are easily expressible using Haskell lists because they consume the same stream while it's building it, which are not expressible using Java streams, or certainly not directly. For instance, they are just in a sieve for computing prime numbers, or a number of game playing algorithms that build a tree or a stream lazily in Haskell, at the same time consuming a prefix of that stream or tree. Those can't be expressed in using Java streams. But it also reduces, the good thing about that is that it reduces the risk of space leaks. The problem in Haskell is that you hold on to too much data and run out of memory. I won't say more about that. The other great thing, not having to do with streams, but complementing them, is array operations. So you can do lots of things in a few operations in Java 8 with arrays. So you can take a number generator, sort of random number generator, and ask for an infinite stream of doubles. No, not the infinite, a stream of at most n doubles between -1 and +1. That basically gives you, you can think of that as a number of steps along the point line, either to the left by some random amount or to the right by some random amount. Get an array of those. And now you can compute in one go, using this array parallel prefix operation, compute all the partial sums. So applying this array parallel prefix to the array A, we obtain here with the sum function, will in the first element will just contain A0, the next one will be the sum of A1 and A0, and the next one will be the sum of those and A2 and so on. The final element will be the position of this particle at the end of the whole run. And this can be computed very efficiently in parallel. And then you can apply, you can turn the array into a stream and map the absolute function on that. So you get sort of the absolute distance from 0, find the maximal one of that, max of that, and extract the number. So you simulate a particle that moves back and forth in small steps, and you get this maximal distance from the point. You could also parallelize the last thing because, yeah, you could put dot parallel there if you want to. So parallel prefix arrays of the parallel prefix operations like the one I just showed here is if this operation is side effect free and associative, like plus and max and min and times and so on, or string concatenation, then the operation can be parallelized as a so-called prefix scan, invented 26 years ago. And that has a lot of applications. You can also compute sum product, to sort, to compare strings, to lexing of strings, to evaluate polynomials and all sorts of things. Can be done very fast in this way. So, and also it's a relatively easy, not completely trivial, but relatively easy to implement. But it's the kind of thing you want to have in a library, not to have to think about every time you want to do something on this. But I think the bottom line of that is that streams and their arrays complement each other extremely well. That the streams can be lazy, possibly infinite. They are not materialized, so they are generated as they are used. They are used once for that reason, and you can build parallel pipelines out of them. Whereas arrays are the opposite. They are eager. They are always there, built eagerly. They are, by definition, finite. They are materialized, stored in memory. You can use it as many times as you want, and you can do these parallel prefix scans. So together, they actually are a very powerful set of tools. And the last thing I want to say here, I think, is that there are some problems. So use one means that they have some expressiveness restrictions. You can't take a wonderful algorithm from a functional programming book and just write it with streams, because typically they'll use the stream twice or something. Then you'll have to materialize it as an array, extract a stream from the array. But I think the purpose of that is, first of all, to avoid to permit easy parallelization, and second, to avoid space leaks. It's very hard to create lazy finite streams at present, which is really annoying, because it wouldn't have to be hard. It's easy to create in .NET certainly, to create a lazy enumerable corresponding to a lazy iterable in Java, and it ought not to be complicated to create a lazy finite stream. But it's very difficult to control resource consumption. So if your application is running on a big server that is always fully loaded with requests from the outside, then it's perhaps a very bad idea to try to use parallel streams on that thing, because it will just hog CPU power from the other things going on. A single side effect, even one that looks rather innocent to begin with, may mess up things completely. And that is sort of deplorable. Never give in to the temptation to store, to cache something to use in the next call of something. It will not work. And sometimes it's possible to meet some cases where actually using parallel hurts performance a lot. I don't know why it doesn't say parallel here. It should say sometimes parallel hurts performance. There's no exercises here, so you won't. You'll have to go to the ITU course to find those. And also, I've discovered something that must be sort of design or implementation bugs. So a wonderful combination of using limits. I wrote a Sudoku generator, not just a solver, but a generator of Sudoku problems, and using a combination of parallel and limit operations there created a very, very mysterious behavior where no output was generated from a stream until 1,024 elements were generated. And the number 1,024 tells you that it's some kind of implementation issue. And of course that looked like it didn't terminate or something like that. And also laziness in Java is really subtle. It's easy to get it wrong, because you are tempted to combine it with things that are non-lazy. So let's take a look at this here, where we try to get a web page as a stream. So as a good well-behaved Java programmers, we use a try with resources statement here. So we create a new buffered reader from an input stream reader from a URL thing, and do that in here, and call the opened buffered reader in, and call the lines method on that, which turns the buffered reader into a stream of strings. It looks beautiful, but it's completely useless, because the try statement will close the reader before it leaves this one. So it returns a stream that's associated with a closed buffered reader. It hasn't read anything at all yet. So the moment I try to consume this string, it will throw an IO exception. So it looks nice, but the eagerness involved in try with and the laziness involved in this operation do not match.
Difficult to control resource consumption, right? I ran into this at some point in time.
Mm-hmm.
I wanted to do some I/O with a parallel stream. which they do not recommend that you do because they tend to take a long time. But what you can do is to create a thread pool, and it will use that. You can make it use that, so you can control. It's these threads that execute
Okay,
that
yeah,
parallel
yeah.
execution.
Yeah, all I've done here is running on the standard default thread pool,
Exactly.
but you can create your own and the number.
And then
Yeah.
you will not take away
No,
threads
no.
from other processes running.
Okay. Yep. Okay, so that was the last thing I wanted to say here, basically. So questions, comments.
We are melted away.
Melted away, yes. It's very, very brave of you to sit here in the afternoon. Yes.
So do you know if these streams and so on, how much will that be rolled out in some of the standard Java APIs like stacks and XML parsing, JSON parsing, stuff like that?
There's a large number of places where this makes good sense, but I have no idea what the level of ambition is, whether it should. So currently it's very sparsely supported like this on this buffered reader. Basically, I think Java should get immutable collections, and then I think some of the stream stuff will be more natural actually. But of course there are already zillions of things like parsing libraries and so on where you would like to see it. Also, streams are by nature linear, sequential, and some of what is returned from an XML parsing is more like a tree. You would also ideally like to have some sort of lazy tree or whatever, but it's much less obvious how this should be done. So I think the design space is probably too large for them to want to guess in Java 8 what is going to how much it should cover.